panel, still continuing the theme of obfuscation, is by Ilya Volkovich, who will tell us about the relations between circuit and minimization.
So thank you. Well, actually, my talk will be, I'm the last one, so my talk will be a combination of, I guess, apologies and saying thank you. So first, thank you for the organizers, I should say. It's a great workshop that you organize here. And now, I mean, I do start with an apology, which is I'm not as skillful in terms of animation as all the previous speakers. I'm just going to use plain simple ones. Okay, that's an interpretation. But I'm going to talk about, as you all said, the connection between circuit obfuscation and minimization. It's a joint work with Valentin and Russell, who I'm happy to have here in the audience. So in this sort of the theme of this workshop, it talks about all kinds of assumptions and thinking for cryptography. I would like to tilt the scale and look about this from slightly different angle is complexity theoretic. What are the necessary and sufficient complexity theoretic assumptions for cryptography, right? So you can actually take it to many ways, and there are all kinds of things touched upon this in the previous days as well, but I would like to focus on something very concrete here, and this is perhaps one of the holy grails of complexity theory. Again, I don't have a holy grail here, but you'll have to forgive me for that. And this is lower bounds. So, you know, in complexity theory, proving lower bounds is the holy grail. But if I want to start this conversation as a cryptographer, the conversation ends pretty fast because many standard cryptographic assumptions already imply strong lower bounds. So basically, if this was it, I had to leave and, you know, say goodbye. The talk ended because, you know, something very simple as one-way functions. Once you say I have a one-way function, you already separated NP from BPP, and if it's a one-way function which is secure against non-uniform, you know, adversaries, you already separated NP from P/poly, which is, you know, one of those holy grails. And it doesn't stop here. You can talk about zero knowledge and all of that. So all of those things already give you strong enough lower bounds. So again, if we want to continue, at least make sense in this line, we should ask the question, do we have any cryptographic primitives that are not known to imply lower bounds immediately? And hint, this primitive should not imply one-way function, which is kind of restrictive, but I mean, I'm going to ask the question, what is that? It's in the title of the talk. What is an example of one of those things that is not known to imply one-way function, but at the same time is not known to have lower bounds? Anyone wants to guess? You ask all the questions, so you want to guess, right?
Indistinguishability.
Oh, that's a good answer. So that's a place, that's never would have guessed. So this is a place when I want to thank Rachel for introducing IO, so I don't have to talk too much about it, but I do want to say a few things. So what is an IO to level the playing field? We want to take a program and transfer into something which is unintelligible, right? So a few days ago, there was this conversation, what should programs look like? Some of you prefer Python, so I'm a C++ person. Here is a C++ program. What does it do? Yuval, do they still teach C++ in the intro classes in my alma mater? Anyone?
It's and numbers.
Well, congratulations. You know, you're what you was called an IO expert. So anyway, if you take the slide of
Security against CDO is not good enough.
it's a instantiation for the random oracle model, right? So if you take this line of code in C++ or Java, it's equivalent, but kind of more broadly in terms of what we want some kind of a procedure which takes circuits, transforms them into another circuits, with the property that if you take two circuits that have the same size and functionality, if you look at their obfuscations, they're indistinguishable. Basically, you cannot distinguish, and I'm actually going to talk about more precisely in a minute. That's kind of the thing that we're exploring. And again, thanks, Rachel, for the great introduction. And for that. So let me talk a little bit more about this. So again, this is the main requirement that we want, but the question that I would like to ask is, you know, what are the necessarily, you know, the question that we've been asking, the necessary and sufficient conditions for those things to exist, but, you know, sort of in particular, we know that IO have had a lot of applications for all kinds of things, cryptography and complexity as one, and at the same time, for the past 15 years or so, we saw numerous candidate construction culminating in GLS. And now, again, the real question is, what are the exact conditions? So now, when you look at that from the complexity theoretic perspective, and it was mentioned, what happens is that unlike the vast majority of cryptographic primitives, you can still get IO even for something like P equals NP. In fact, this is, something that you get in some automative way, right? If P equals NP, what you can do is you can take a circuit, you can learn it and output the smallest canonical form in that. So this is, again, doesn't happen in one-way function. You don't have that. So this is already something which is interesting. And now that kind of brings the question, well, where does IO live in terms of that? And to answer where we live, there is no other place to live than in Pagliazzo 5 worlds. So we live in one of them. So we could say that we live somewhere. Again, apologies for my animations. I cannot make those nice animations that we had before, but I'm going to take it plain. So the first one is algorithmic. So again, this is what we just discussed. If basically P equals NP or NP is BPP, we get the ultimate obfuscator. So of course it exists, it can live nicely in algorithmica. What happens if you go down the list? So heuristica is the place when NP hard function, we have NP hard in the worst case, but it's easy on average. In particular, we don't have one-way functions. So by combining some previous results, in particular, Komagotsky et al., it's a good reference. If you have IO and one-way functions, you basically get that NP is an IO BPP. By the way, that's not to confuse. This small IO is infinitely often. This IO is obfuscation.
IO and one functions doesn't exist.
If you have IO and if you have IO, okay. If you have IO, yes. Should be a note here. Yes, if you have IO and you don't have, basically, if you have IO and this doesn't happen, you have one function. So basically, you cannot have that. So in particular, IO cannot live in heuristica. Okay. For the exact same reason, IO cannot live in Pesseland because you don't have one-way function. So what's left? Going down the rabbit hole, minicrypt. So what happens in minicrypt? We do have one-way functions, but we don't have, say, public key cryptography. At the same time, Sahai and others have shown that if you have IO and one-way function, you can actually get public key cryptography, which kind of means that you don't get IO either in minicrypt. What's left? What's left is where I think if I ask most of you here, you're all going to say we live there. We live in cryptomania. So cryptomania is where cryptography is possible. We have one-way function, public key encryptions, all the nice things. And the recent work, the great work of Rachel and colleagues make it a great argument that IO may exist. So I'm going to apologize for you, Rachel, because I'm only going to put it in yellow because it's still under assumption. Here it's not, but here it's under assumption, so you're going to forgive me. So in conclusion, what do we have? We have that IO can only exist in algorithmic and cryptomania, although there is this new trend to try to define a new sixth world, which is called obfuscatopia or something like that, but it means it kind of spread in between these two. And the main issue here is that the assumptions for IO are non-trivial to wrap around. Sort of, we want, as a community, as in cryptography, to live in cryptomania, but if you're not careful enough, you may end up very well go and find yourself in algorithmica. This is kind of what makes, I think, IO non-trivial. Questions? Yes?
But if you just say your IO is computational, then it's definitely cryptomania, not algorithmica, right? Because algorithmica IO is statistical.
Well, I mean, if it's statistical, it's also computational, right? I mean, it's a stronger, you get the ultimative IO here, which in particular is computational, right?
So strictly computational.
It's not, well, it's not clear how you make, well, how do we make something, computational and not, you kind of have to be precise about that, right? But other than that, this one is also computation that you get here. Good. More questions? So
your knowledge is in the same situation, right? But you don't have to go to fancy things like IO to find something.
So, this is not, again, the only object, as you said, but this is one of a few objects that kind of share the property, of course, right? Good. Yes. So actually, let me switch gears and talk about something else, which is a little bit outside of the realm of what people traditionally do in cryptography, but it's still very, very relevant. And this is the minimum circuit size problem. So we heard a few talks on the topic. And actually, this is the place to thank Hannin for giving a great introduction about this topic. So I don't have to talk too much about it, but I still want to say a few things. So what's the problem here? We're given a truth table, a string of length 2 to the n, and we give a size, a parameter. And what we'd like to know whether there is a circuit of size S that implements this truth table. So there's an important thing to emphasize here is that your input size is not n, but 2 to the n. This is kind of atypical. Usually n is the input size. So just to realize that this already gives us something relatively straightforward, which is that MCSP is an NP, right? So why is it in NP? Because first of all, you can guess the circuit, and then you can do is check that the circuit actually computes the truth table. Again, we can be efficient and to the end. So this is the thing that we know, and this is unfortunately one of the few things we actually know, because all the other things start getting convoluted. So one important property about that MCSP, nonetheless, is that it's not a bug, it's a feature. So a line of work started by Volkovich and Zborov by subsequent work pretty much showed that any one-way function can be inverted by BPP algorithms and MCSP oracle, right? So, I mean, this is, since it's a cryptographic audience, I probably should correct myself. Instead of BPP, I should say PPTM, but you can pardon my French, I think, right? I don't want to use FBPP because it was already. So the point is, if I have a randomized algorithm with an MCSP oracle, I can invert all those, I can solve all those nice problems like integer factorization, Diffie-Hellman lattice problems, and FCP. You know what FCP is? It's your favorite cryptographic problem. So you can do all of this with an MCSP oracle. And kind of to cycle back, there are some nice connections here. So this, may give some ideas that MCSP is maybe way too powerful. Maybe it's even NP complete. So that's one of the questions. What is the exact complexity of MCSP, right? So, okay, and the first thought was, let's try and see whether it's NP complete. So this is a place when you have to say thank you to Ryan and other people who've shown that if MCSP is actually NP complete in the standard sense, what we get is X not equals ZPP. So sort of, again, to understand this properly, while most of us do believe that X is equal to ZPP, our current techniques are far away from establishing that. So the conclusion is that even if we believe that MCSP is NP hard, it will take us some kind of non-trivial techniques and non-trivial breakthrough to actually show something like that. So based on that, there was sort of a suggestion that we should perhaps treat MCSP as an NP intermediate problem, those problems in between. And in fact, there are great things to support it, results by Allender and Das that show that you can solve Grail isomorphism. And in fact, SZK, the class of problems that we all like and have all those nice cryptographic problems, we can solve that with BPP to the MCSP. So that's nice, but the question kind of remains, okay, maybe MCSP is still hard, but maybe out of a broader notion, right? Maybe you have to expand your reduction, a ZPP reduction, a BPP reduction, maybe a P/poly reduction. That's a conjecture that perhaps, okay, if we can't achieve the usual, reduction, maybe we have to broaden the reduction and then we can show hardness of MCSP. This is a conjecture, and now sort of to tie it back to I/O, turns out to be interesting connection. There was observed previously in a different context in a paper by Komogotsky et al. In the context of one-way function, which is the following connection. Suppose I/O exists, then MCSP is in BPP if and only if NP is in BPP. Sort of, this has this flavor of completeness, right? If I have I/O, then MCSP, this problem bears the whole weight of this NP plus. It's not sort of the best thing that we want, but this already gives us the flavor that connects things together. So just maybe to wrap it up, to wrap yourself around a little bit for intuition, MCSP and BPP is kind of morally equivalent to, there is no one-way function. If you want to think about it this way. There are some gaps here, but sort of this is the moral thought. So I do want to say two more words about I/O before I give you the results. Questions about that? Again, I'm not going to introduce I/O from scratch, but I do want to make a few sort of specifications in terms of what do we want from an I/O. So the main properties that we want is one, correctness, and we actually want to talk about more broadly. So usually when you talk about I/O, when you obfuscate it, you want the obfuscated circuit to have the same functionality. This is what's called a perfect obfuscator, but you can also look at what's called an imperfect obfuscator, like absolute imperfect. What does it mean? It means that, well, you're going to get what you want with high probability. So basically with probability 1 minus epsilon, the obfuscated circuit has the same functionality, but with probability epsilon, you can get all kinds of garbage inside. So for example, if epsilon is at 0, it's a perfect I/O. So this is useful. And now one more thing, which is sort of the other requirement of an I/O, which is what's called security. So we want to define it broadly. So what is security against a class of algorithms? So imagine an A is a class of algorithms. So security means the usual thing. If you take two circuits which have the same size and the same functionality, then they're indistinguishable. Okay, this whole crazy thing means they're indistinguishable, or the distinguishing probability is something like delta. So typically we want delta to be small, negligible. But as we will see, I deliberately put here delta. It doesn't have to be. There's a certain trade between epsilon and delta for which we can still work. So now, why do we want to look at the class of algorithms? The two typical scenarios are when A is taken to be all the efficient algorithms. This is what corresponds to computationally secure I/O, or sort of the high end of it, which is A is the class of all algorithms, very inefficient, doubly, triply exponential. In this case, this is the class of statistically secure I/O. So the reason I want to talk about security for a class, because we're actually going to look at something sort of in between, something which is between this BPP and everything. Questions about the definitions? So again, what you should be thinking about when I say imperfect and secure is that sort of the extreme case, the usual thing is epsilon and delta being negligible, but you can still think about them being constant. There is a trade-off which I'm going to mention. Think about epsilon being small and delta being small is still going to work. So now I can actually tell you what the results are, the connections between I/O and MCSP, and hopefully answer some of the questions here. So let me start. And the first flavor of results that we show is lower bounds from I/O. Namely, if you have I/O, you get lower bound. That would be more specific here. So the first set of results is, suppose you have a perfect I/O which is secure against P/poly, secure against non-uniform adversaries. So you get that NEXP is not P/poly, and you also get basically super polynomial lower bounds from NEXP, and you also get what's called fixed polynomial lower bounds for NP. You cannot compute NP by circuits of size n to the k for any k. This is what happens if you have a perfect I/O. Now, if you have an imperfect I/O, you get something weaker. So you get super polynomial lower bounds against MA. That's fixed polynomial lower bounds against MA. So just for context, because I'm going to repeat it, next is the exponential version of NP. Questions? We discuss this a little bit and be glad to hear questions. So as far as we know, this is the first consequence of strong lower bounds from existence of I/O. And if you know something else, please let me know. It will be curious. And now we want to compare it to what we know kind of unconditionally. So unconditionally, without any assumptions, we have lower bounds for MAX. What is MAX? Is the exponential version of A, and next is the exponential version of NP. MAX is the exponential version of MA. And we also have, for the low regime, we have bounds, fixed polynomial bounds for MA/1. This is thanks to Rahul. And now one thing I'll let you know, if you kind of look at this MA and MA/1, it might seem a really small thing. This is really one bit of advice, but I'll tell you that you wouldn't believe how much time the community spent on removing this one bit of advice. Like, you wouldn't believe it. So, I mean, you can think about it. Well, maybe I/O is a big thing to assume, but I/O allows you to do that in particular. I mean, we're talking about all kinds of applications. So one of the applications is to remove one bit of advice. And hopefully there are better ways to do it, but at least that. And the other thing that I want to mention, that while all those bounds and others on this slide, again, we believe them to hold unconditionally. Sort of, we believe that NEXP is not in P/poly and everything. We believe it to be held unconditionally. This state of affairs is kind of sad because it looks like we're nowhere near proving any of these bounds, including this bit of advice. We're nowhere near to doing it unconditionally. And if you actually want to read more about it, I would like to thank Ryan for writing a good review, a good survey about that, sort of what the problems here. Questions? Yes.
You get more mileage if you have some exponential security for the IO.
So we didn't actually look. I mean, I suspect you can get some kind of a parametric thing. I suspect you can get more. We didn't actually look at this. I suspect you can do more. I mean, I would say yes, but we didn't actually look at that to formulate. More questions, Marco?
Is that any uniform versions of these lower bounds of P?
Wait, one more slide. I tell you what happens there. Very good. Yes, you know.
What do you mean by the best known unconditional for strong knowledge?
So if you ask yourself, what's the lowest in terms of what's the lowest class for which we know super polynomial lower bounds? MAS. So I mean, again, unconditional. Again, there are other better bounds that we know sort of conditionally, but then you can start asking the question, IO is that versus that assumption. But sort of unconditional, this is the best thing that we know. The smallest complexity class for which we know.
Question.
Question.
So if P is equal to NP, then we have IO.
Yes.
So doesn't that contradict the second?
You actually get stronger lower bounds if you assume P equals NP.
Well, yeah, so if P equals NP, you get those kinds of lower bounds for P itself already. You get that P is not in size n to the k, into the complement point. No questions? So this is again, if you assume secure or insecure, perfect, imperfect, or if you assume perfect or imperfect IO, which is secure against non-uniform adversaries. And the next thing is what happens, as per Marco's question, what happens if you assume security against uniform? So this is kind of the next thing that I want to talk about. Well, suppose now you have IO which is perfect and secure against sort of uniform adversaries, right? So you get a couple of things. So one thing which I mean I find surprising, but Valentin actually decided that it was decided that it's worth mentioning. I actually found it surprising when you mentioned that, is that the following: if you have such an IO that if MCSP is in BPP, you get that NP is in ZPP. Sort of think about that. You start with a problem in NP, it's in BPP, then the whole class collapses down to ZPP. I know that the people in cryptography don't care much about the difference between BPP and ZPP, but just appreciate it for the moment. Right, so
I appreciate it.
thanks. So now the interesting thing is that, again, maybe the next bullet will help you appreciate it better, is that, well, you can actually use this result to show something else. You can use the result to separate ZPX from BPP. So ZPX is the exponential version of BPP. So let me, again, questions about the result, let me discuss that in the broader context. So basically, what do we know here? So unfortunately, so we have those hierarchy theorems for space and time. Unfortunately, we don't have those theorems for randomized complexity class. We don't have what's called for semantic classes. But nonetheless, if you want to separate ZPP from ZPX, basically, this is the exponential version. This is something which is relatively easy to do. Now, if you kind of start turning the heat a little bit, we don't know to separate NEXP from BPP, or more even so, X to the NP from BPP. This is a bigger class, a superclass. So we don't know how to do that. We don't know how to separate NEXP from BPP, and even more so, we don't know how to separate ZPX from BPP. ZPX is a subclass of X. So this is an open problem which is kind of lying around. And what we show is that if you assume that we have computationally secure IO, then we get those separation. We get basically this one. So this is again another application. This is better than 1 bit of advice. I think it's been lying on the street for much longer time. And kind of from that, there is perhaps one reason why it's been so hard. There is an oracle under which all those classes, basically BPP, NEXP, and all of that, everything we're trying to separate, that all those classes are kind of equal. And if you kind of plug it back, what you get is you don't get something new, but I think it's interesting. You get that relative to that oracle, oh, we don't have an IO. So that's not a new result. Of course, you're going to tell me that, pick any pestilent oracle or something like you wouldn't have an IO other, but I think it's a nice connection. So you can exclude IO by looking at oracle, which sort of collapses some polynomial, some complexity classes. And kind of brings me to the next point, something that was discussed here earlier. I don't know the answer to that question, maybe you do. What happens with a random oracle? So do we have IO with respect to random oracle? So if, for example, you prove that those things are equal with respect to random oracle, you show that you don't have an IO with respect to random oracle. Not sure if that's the best way to do it, but I think it's a nice.
How do you define IO with random oracle? Like, does the obfuscated circuit has access to random oracles?
So your circuit is an oracle circuit, basically, right? And your output circuit is an oracle circuit. Usually, pretty much everybody has an oracle can access O, right? How much time do I have, Yuval? Okay, it's good because what I do want to do is I want to give you a little bit of a flavor here, but I do want to talk about the last point, and this is sort of the other direction, how MCSP can empower IO. Sort of the thing that fuels this whole, all those results is the following connection. NIO is statistically secure, any IO, only if it's secure against BPP to the MCSP. So this is the reason. If you think about BPP to the MCSP, it's a superclass, syntactic superclass of BPP, and of course, it's a subclass of all the possible algorithms. But as it turns out, is that statistical means it's secure for any possible algorithm. But it actually means that if you want your best distinguisher, the best distinguisher doesn't have to live high in the sky, like, I don't know, X space or something like that. It lives sort of relatively down on Earth in BPP to the MCSP. So this sort of fuels it. And sort of as some conclusion, you can also extend the result that we had for imperfect IO. So if you have an imperfect IO, then the same thing holds true. MCSP is in BPP if and only if NP is in BPP, right? We previously knew how to do it for perfect. It's extended to imperfect. So a few remarks here that I would like to point out. So we talked about IO, and in all of those results, we kind of assume that we have IO for all circuits, but as it turns out, you don't need to get those results. You don't need an IO for all circuits. It's enough to have IO for much smaller circuits like 3 CNFs, and all you need is the circuit class for which the equivalence problem is going to be hard. And as it turns out, these are much smaller, for example, 3 CNFs or bitwise polar. But I think the surprising thing is that it's enough to consider monotone class. If you consider monotone depth-3 formulas, again, monotone is without no. If you can obfuscate monotone depth-3 formulas, you already get all those results. Again, you get the exact same results for any of those classes. But we just mentioned that all those classes are much smaller. Typically, as we heard, what happens is that all the existing candidate constructions kind of start from NC1. You go to NC1 and then you boost. So all those classes are much smaller than NC1. That's already enough to get those bounds, all the things that I talked about. Questions?
Is this all still true if you just have non-IO?
If you have what, sorry?
Null IO. I mean, IO just for circuit that doesn't apply. Separate.
Now, okay. So yes, I mean, now, okay. So I didn't hear what the last one was. Sorry. So yes, so basically this is what, so I mean, you do need this. You do need the security. You do need the security, right? You don't need the security thing that says, okay, if it has the same functionality, it has to be the same, right? It's not. You need the security requirement. You're not going to obfuscate everything, but you do need the security requirement, right? Make sense? No questions? And let me just mention, in terms of epsilon delta, remember the security and imperfection. So you don't have to be perfect. You don't have to be negligible. It's enough that your security is less than 1 minus epsilon squared, when epsilon is the level of imperfection, right? So basically, you can have an slightly imperfect IO, which is somewhat secure, and it's still all going to hold. All these things are going to work. Questions, concerns, complaints? So I would like to maybe give you one taste, but this is another place when I do want to say my one last thank you, as I learned recently, literally a few days ago, from talking to Moni and Guy, that you can actually extract that result. If you dig up a little bit into one of their proofs, you can actually extract that result. You didn't think about it in the context of MCSP, but if you take your result, a piece of your result, extract it, and put MCSP on top of it, you can actually recreate that. So thank you for that. Now, let me just maybe give you one flavor of one of the proofs of one of the low bounds. And it will be, and I like to kind of start by proving something very, very weak. And this is the following. Suppose you have imperfect statistically secure IO. Now I want to show that AM doesn't have fixed polynomial size circuits. Okay, how do I do that? So the starting point goes back to a fundamental, I think, the first result that kind of started exploring those impossibility results for IO. And this is the result of, thanks Guy and thanks Shafi, Goldwasser, Rothblum, that basically much showed that if you have imperfect statistically secure IO, then the polynomial hierarchy collapses to AM. This was the result. Among other things, they've shown that. Now, how do you get from this to this? This is an easy exercise and diagonalization. What you show is that polynomial hierarchy does not have circuits of size n to the k, right? This is a standard diagonalization that we do. So how do you put the two together? Well, if you have statistically secure IO, PH collapses to AM for better or for worse, which means that now AM doesn't have those circuits either. This is how you get that. So let's conclude what we have so far, that if you have statistically secure IO, that AM doesn't have circuits. But this, given Goldwasser, Rothblum, this result is not surprising anyone. Specifically after their work, nobody, I think, believes in statistically secure IO. It's like I could have written here, this is true if hell froze, or this is true if there is snow in California, right? This is kind of, all those kind of statements. This is what it looks like. So let's move a little bit to something slightly more important, slightly more interesting than that is, again, let's plug in our result that says you have statistical security if and only have security against BPP to MCSP, right? So if you plug it, you can just substitute statistical with stat security. And what you get is that something slightly interesting. If you have an imperfect IO, which is secure against BPP to the MCSP, then we have lower bounds against AM. This is maybe slightly more interesting. And now to put the fine thing here, I want to actually go from this to our result, which is if I have an IO which is secure against P/poly, I get lower bounds. I want to go from this to this, and this is done by the standard two-pronged approach we use in complexity theory, also known as the win-win argument. And the interesting thing is that it's conditioned on the complexity of MCSP, namely two cases. If MCSP is not in P/poly, we're already done because MCSP is an NP, which is an AM, so we're done. AM is not in P/poly. The other thing is more interesting. What happens if MCSP isn't P/poly? And he says something interesting happens, I think. MCSP in P/poly means in particular that BPP to the MCSP is in P/poly. This is a standard Adelman trick to do that. And now let's just take 30 seconds and read what it says on the slide, right? Shall we? What is it that we're trying to do? We're trying to say that if imperfect IO is secure against P/poly, then AM has lower bounds. But what did we have now? Under this assumption, MCSP is in BPP and BPP to the MCSP is in P/poly, which means that if you're secure against P/poly, you're in particular secure against BPP to the MCSP, because it's a subset of that. And now we're going back to the corollary, which says exactly that. If you're secure against BPP to the MCSP, you have lower bounds. And now that's the place where you combine and say, look, we have two cases. You're either not in P/poly or here, which means that either way, you're not in size n to the k. Okay, let me just finish one remark and say that if you want to get it, if you want it in the perfect case, you have to use another observation that pretty much says that if you're secure against, if perfect, you're secure against this UDP to the MCSP, the polynomial hierarchy collapses all the way to NP, not just AM NP. This is how you get NP in the case of perfect security. So actually a good time to stop, and let me summarize. What we've shown is that imperfect or perfect IO secure against non-uniform circuits. Non-uniform point circuits imply non-trivial lower bounds, and sort of there are a few interesting questions, in particular what Mark was, can we derive lower bounds if we assume security against uniform attackers? And sort of the other thing which I think is sort of a way to interpret these results, right? If you go back, maybe if we go, just let me go back here and go back and sort of think about like here, how should we interpret those lower bound results? So, those lower bounds are hard. So one way to interpret would be to say, life is hard, complexity is complicated, cryptography is even more complicated. So let's do something practical like machine learning. That's one way to interpret those results. I think a better way would be to say, whenever we construct propose new candidate IOs, we should be conscious, right? We should be conscious that whatever we're going to do, we're talking about eliminating assumptions, right? Whatever we're going to do, we should be conscious that if we eliminate too many assumptions, we're actually going to hit this lower bound barrier. So we have to be conscious about that. And this is sort of the takeaway that I think is saying here is that I have discovered a truly marvelous proof of this lower bounds, which this candidate IO construction is too unconscious to contain, right? So when you think about constructing a candidate IO, you typically don't think about lower bounds, but that's the thing. Once you do that, apparently you do one and do the other, right? So this is the thing that I wanted, the message I wanted to say. And there are other problems which are sort of related, which I'm just going to write it down and I'm going to talk about in the interest of time. So thank you.
Thanks, Ilya, for the great old school talk. And yeah, we'll take it for the questions offline and stay right here. We have now a panel assumptions in cryptography and complexity theory. Stay tuned.